You know, for years, the story of AI has felt pretty simple. Bigger is better, right? More data, more computing power, bigger and bigger models. But what if that's not the whole story? What if we've been chasing scale when we should have been chasing structure? Today, we're looking at a brand new kind of AI that throws a wrench in that whole bigger is better idea, and it points to a much smarter path forward, one that's actually inspired by our own brains. And it all kicks off with a simple puzzle.
So here's our real head-scratcher. Our most powerful language models, these absolute giants. They can compose poetry, they can write software, they can do all sorts of incredible creative things. But ask them to solve a genuinely tough Sudoku puzzle, a task that's just pure step-by-step logic. And they just fall apart. They fail, and they fail spectacularly. So what gives?
Well, the problem really boils down to this. LLMs are absolute masters of pattern matching and language. That's what they're built for. But their core architecture is fundamentally pretty shallow. They really struggle with the kind of deep, multi-step reasoning you see on the right. They've developed this workaround called chain of thought, where they kind of talk themselves through a problem. But as this new research shows, it's a really brittle strategy. One wrong step, one little slip-up, and the whole house of cards just collapses.
All right, so if just making models bigger isn't the answer, what is? Well, researchers at Sapient Intelligence decided to look for a better blueprint. And instead of trying to build an even bigger computer, they took a look at a much older and way more efficient one, the human brain. It turns out it's a masterclass in deep, logical reasoning.
The brain's incredible efficiency really comes down to a few key ideas. First up, hierarchical processing. You've got different parts for different jobs, some for high-level abstract plans, and others for the nitty-gritty details. Second, there's temporal separation. That big-picture planning, it's slow and deliberate, but it guides the super-fast, almost reflexive calculations happening at the lower levels. And finally, and this is so important, recurrent connectivity. These constant feedback loops let the brain check its work, spot mistakes, and change its plan on the fly. This structure is the secret sauce.
So, taking inspiration from this incredible biological machine, they built something totally new. It's called the Hierarchical Reasoning Model, or HRM for short. And it's an AI that's designed from the ground up to actually reason, not just to mimic patterns.
At its heart, the HRM is a direct reflection of the brain's structure. It has two main parts that are constantly talking to each other. You've got a high-level module for the slow, abstract, big-picture planning, and then you've got a low-level module that does the fast, detailed number crunching. They work in tandem to chew through a complex problem.
Probably the easiest way to get your head around this is with a manager and worker analogy. Think of the high-level module as the manager. It looks at the entire problem, comes up with a strategy, and breaks it down. Then it hands off one specific task to the low-level worker module. The worker gets down in the trenches, crunches the numbers, and reports back. Then the manager looks at the progress, updates the plan, and gives the worker its next assignment. It's this continuous loop of planning, doing, and checking.
Now, this whole two-part system does something really, really important. It keeps the HRM from getting stuck. A lot of AI models, especially ones that have a kind of memory, will find what they think is the right answer and then just lock onto it. Even if it's wrong, they can't backtrack. But HRM's manager can basically hit a reset button on the worker, telling it, nope, that path is a dead end, let's try something else. This prevents it from getting trapped in a mistake and lets it explore problems with real depth.
Okay, so the theory sounds amazing, right? A brain-inspired AI. But the real question is, does it actually work? Well, the researchers decided to find out. They put RHM head-to-head against some of the toughest reasoning challenges out there, facing off against models that were thousands of times bigger.
First up, let's go back to that Sudoku problem. They created a special dataset called Sudoku-Extreme, packed with puzzles so hard they require a ton of searching and backtracking. They gave it to some of today's leading AI models, and the result was a complete and total wipeout. 0% accuracy. Zilch. Nada. The models just couldn't do it. But then, they ran the test with HRM. And on the exact same puzzles where every other model got a big fat 0, HRM solved over half of them correctly. Let me say that again. From 0 to 55%. This wasn't just a small improvement. This was proof of a totally different kind of reasoning capability.
And it wasn't a fluke. They tried another brutally hard task, finding the one single shortest path through a really complex maze. And again, you see the same story. The big models? Zero. They were completely lost. HRM, it found the perfect path nearly 75% of the time. Just incredible.
Okay, so it's good at puzzles. But what about general intelligence? Well, they tested it on the ARC-AGI benchmark, which is designed to measure an AI's ability to solve new and abstract problems on the fly. And once again, HRM came out on top, beating models way larger than it. But the reason it can do this is where things get truly wild.
Get this. HRM achieved all of these stunning results with just 27 million parameters. Now, to put that into perspective, the models it was crushing have tens, sometimes hundreds of billions of parameters. It is, and I am not exaggerating, like a go-kart lapping a fleet of Formula One cars. It's just not supposed to be possible. And if you thought that was crazy, check this out. It learned how to do all of this from scratch with only 1,000 examples. No pre-training on the entire internet. It learned pure, abstract reasoning from a dataset so small it's almost comical. This level of data efficiency is it's off the charts.
So you're probably wondering, what does this thinking even look like inside the machine? Well, the researchers gave us a peek. Here, you can see it working on a Sudoku puzzle. It's starting its process, exploring the board, and trying out a few numbers, almost like a person would.
But watch this. Here, the model realizes it's made a mistake. It's hit a dead end, a conflict shown by the red cells. And this is the magic moment. Instead of getting stuck, it recognizes the error. This is that manager module stepping in, telling the worker, nope, that didn't work. Backtrack. Erase that last move. It's actively searching, just like we would. And after a few more cycles of this, exploring a path, realizing it's wrong, backtracking, and trying a new one, boom, it finds the correct solution. This isn't just spitting out a memorized pattern. This is a real, dynamic problem-solving process happening right before our eyes.
So yeah, the performance is just incredible. But the implications of this work are even bigger. This isn't just about a new, clever model. This could be a fundamentally new direction for artificial intelligence.
There is a quote in the paper that just nails why this is such a big deal. Today's big models treat reasoning like it's just another form of language, that whole chain of thought thing. But you and I don't think in full sentences, right? Our thoughts are flashes of insight, manipulating concepts silently in our heads. Well, HMR works the same way. It performs what's called latent reasoning inside its hidden layers, which is a much more natural and efficient way to actually think. And this might be the most jaw-dropping discovery of the whole thing. After it was trained, the researchers looked inside HRM and found that it had spontaneously organized itself to look just like a mouse's brain. The manager module developed a complex high-dimensional structure. Think of it as a rich, flexible workspace for abstract ideas. The worker module developed a simple, low-dimensional one, perfect for focused execution. Nobody programmed this in. It emerged because it's the most efficient way to solve hard problems.
And that really brings us to the core message here. HRM's success proves that brute force scale isn't the only way forward. In fact, it might not even be the best way. By creating these efficient, elegant, brain-inspired structures, we can build AIs that are not only smarter at reasoning, but also unbelievably more efficient.
This research really throws a challenge flag on the entire bigger is better philosophy that's been driving AI development. It suggests the next massive leap forward in AI might not come from a model with 1 trillion parameters, but from a much smaller one with a much smarter design. And it leaves us with one huge, fascinating question. Is the real future of AI not about being bigger, but about being fundamentally smarter?